Okay, awesome. Thanks so much for the invitation. I'm really excited to be here. A lot of great talks, and we will be talking about interpreting latent spaces and I guess, so one thing that we might be able to talk about later at the discussion is, I'll call them representations rather than latent spaces. Maybe there could be differences in the terminology there, but kind of thinking about a similar framework from what we've been talking about. But when invited to give this talk, because it was focusing on human neuroscience and behavior, I'm actually going to tell you not about neural activity, and instead some new work that we've been doing in understanding and building representations of behavior. And we have been doing a little work in humans, so I'll start with that, and then we'll kind of talk about animal behavior more broadly and some new methods that we have for that. Okay, cool. So I'll just start by acknowledging the crew and the team that contributed to the work that I'll talk about today. So I have a number of folks from my lab that there's a few papers that I'll talk about that did a lot of the work throughout. And then the human work that I'll describe is a collaboration with Alex Herman and his team at University of Minnesota, as well as Beckett Ebbets here in Montreal. So they're also an important part of at least the first half of the talk too. All right, so I'll go ahead and just jump right in. So a lot of the motivation of this work comes from the fact that when we're studying behavior, a lot of us do things, at least in neuroscience, with complex animal behavior, but also studying humans or any sorts of activities that we might do throughout the day. There's many different time scales of factors that can influence activity and behavior within one's day or even over smaller chunks of time. So we're really thinking about this problem as, on the order of seconds or minutes, maybe the activity that you're doing is kind of deriving or constraining the sorts of activities and behaviors you might observe, whether it be walking or drinking a glass of water. But of course, if we kind of zoom out and now look at an entire day instead of just a minute or a second in time, we see throughout our day there's many different things that we do, and then throughout the day, our activity or attention or energy levels can wane. And so even if we're doing the same behavior, the way or the distribution in which we carry out that behavior could actually be different depending on other factors like the time of day. And then, of course, if we zoom out even further and we consider really long time spans, we can imagine that our behavior as we move from a child to adult, of course, we're going to see very different distributions in those behaviors as well. Okay, so if we also just kind of zoom in on what this looks like in the context of animal behavior, because I'll also use this as an example, we can consider like a standard behavioral setup that a lot of us have been hearing about over the course of the meeting, where you might have some tracking of animal behavior, maybe even pose tracking, so you have high dimensional pictures of the kinematics. And then there, of course, on the order of seconds or kind of individual frames, you might care about what is this animal doing, right? What are the actual activities? And of course, over the span of hours, it could be something like the time of day. We know that mice are more active at night, so that should change their distribution of behaviors. And then, of course, the long time scale, we have similar things like age or maybe even disease progression, as well as maybe the strain of mouse. That might actually change some aspects of its activity or its behavior. Okay, so with that sort of motivation in hand, the main kind of goal or approach that we wanted to take here, very much in line with what we heard about, in the earlier talks, is this idea that we can, maybe get some time series or some measure of those behaviors. In this case, maybe we can consider the animal example where we have key points along the mouse's body, and then we're tracking all of those key points in time, right? So we have this very complex, high-dimensional picture of what the behavior looks like. And then what we'd like to do is to be able to build a model, hopefully, maybe with either limited amounts of labels or potentially unsupervised, that will give us some representations or maybe some compression of the data that allows us to then read out a number of different pieces of information that we might care about. So for instance, from those learned representations, we could predict the strain of mouse. But then in addition, we could also predict, is it grooming or is it huddling with another mouse? So really being able to read out those very short time scales of the behavior and activities, doing activity-based segmentation, but then at the same time, over the whole sequence, maybe finding some structure and some picture local features as well as the global ones. So often when you focus on getting a very good and accurate predictive framework, you kind of lose the ability to understand how those behavioral distributions at the global level are actually changing. So it's often that you're trading off one for the other. And so one challenge is how do you get both, right? And then the second is that when we're dealing with free behavior, behaviors that aren't instructed, right? The animal is just moving around or you're doing your thing, then oftentimes it's really hard to predict into the future, right? Because there's no underlying kind of deterministic dynamics that will govern the system evolution. And so I'll tell you, I'm going to first talk about a general solution to this problem that's really going to tackle this first challenge. And then I'm going to talk to you about some new work that we've been doing to try to also address this second one as well. Okay. So to address the first challenge of being able to form a multi-scale representation of behavior, we've introduced this framework that we call BAMS, so bootstrap across multiple scales. The multiple scales part should be kind of self-explanatory given what I've said thus far. And then this idea of bootstrapping is kind of bootstrapping is used in many other contexts, but in this case, what we're actually referring to is the introduction of a temporal contrastive learning objective, which yes, in other contexts is called like bootstrapping, okay? All right, so I'll go ahead and just describe the model. As I described before, we're gonna have these sequences, so a multivariate time series data set that has many different attributes of underlying behaviors and actions. And so here I'm just showing the different key points that we're feeding into the model. So what we'll do is we'll take in some window in the past. So we're using temporal convolutional networks, so they're actually causal, but you could still imagine some of this being done in a non-causal system. But essentially what we're going to do is we're going to pass in some history of the sequence or of the data into our encoder, and really the goal is to be able to, so we're going to have a latent representation, and we're going to actually explicitly divide it into these two different spaces. So we'll have a short-term latent space, and we'll also have a long-term. The short-term encoder is going to see a much smaller receptive field. So it's only going to see a little bit of time into the past. It's not going to use more global structure or long time sequences to form its embedding. This long-term encoder is going to look over a much longer sequence. We're going to then find an encoding, concatenate them, and then here I'm just kind of showing this idea of the temporal contrastive learning objective, which basically just says that points that are close in time should also be embedded to nearby points within the latent space. And so our short-term encoder and long-term have different windows over which they bootstrap in order to find that sort of temporal stability within the representations. Okay. And so then, once we concatenate, once we do our bootstrapping and temporal contrastive learning, then we'll finally feed those representations into our predictor, and then the goal is just to predict the key points over some future points in time. That's very fancy. Okay. Okay, cool. So So hopefully the model is clear. We have, these two different latent spaces where we're encouraging similarity in time in the latents at these two different scales. And we also have different receptive fields as well. And then those are being used to predict future actions. So the first example or data set that I'll describe that we apply this to is coming from a human behavioral experiment. So here we have 1,000 participants that were recruited to play this game. It's a 3-arm bandit task. And so what that basically means is there's going to be 3 different possible choices that the person can select between. They've been told that their goal is to maximize the reward, but they don't know anything about, the probability of getting rewards from any of these different arms, or in this case, like a deck of cards. And so we have 3 different arms for which you can get rewards. It's a binary reward, so there's going to be some probability associated with each of the arms. They have to kind of track what's going on with the task in order to try to build some predictive model of which of these arms will have the highest payout or highest amount of reward. And then the goal would be to, actually select that action. So we have 1,000 participants. And they do 300 rounds of this next step action selection task. And then we're recording their actions, so which of the 3 different options did they choose, as well as the reward that they get. Okay, and as I said at the beginning, this is joint work with Alex Herman at University of Minnesota and Beckett Ebbets. Okay, so this is sort of just a glimpse into the data set. This is a cool visualization that my grad student created. It's moving a little quickly, so I'll try to parse through it. So essentially on top, we're just showing what is the reward probability that's associated with each of these different arms. They're all independent, so they don't necessarily add up to 1, right? But they are governed by a slowly moving, like, stochastic drift process. And so at different points in time, the highest rewarding arm can switch. And so the participant should be able to eventually track that over time and kind of change their actions accordingly. So then below this, we're also showing the output of the model. So what the prediction of future choices that the model is actually building, as well as this is just showing the kind of probability of those different choices and the outputs of our predictive model. Over on the right, we're also showing the like a PCA embedding of the latents, and showing just how, for a given participant, as they're moving in time, how this is actually kind of tracing out this trajectory within this latent space. Oh, sorry. So, okay, so just to validate the model, we wanted to start by just understanding how accurate this model is at being able to predict future choices. Overall, we're able to achieve like 70% or 76% accuracy, and this is training on 80%, so 800 of the participants, holding out the remaining 20%. And so when we actually get a 76% accuracy of choice prediction, that's on these completely held out individuals' behaviors. In addition, we find, adding in the contrastive learning and adding in these different spaces, both the short and the long term, help to kind of provide even more accurate predictions overall. Okay, so I'm not claiming this is a very interpretable latent space, but this is the latent space that we get. And we are digging further into this data set and really trying to understand it. But through this kind of disentanglement between the recent past and then this longer term history, we're able to kind of zoom into this long-term embedding, and we can start to see some signatures of decision making. So what we find actually in looking through the trajectories within this latent space is that there are some individuals that even if they have evidence that tells them, like they don't get a reward, so they might need to switch, there are people that are very persistent in their choices and just keep on choosing the same action over and over. And what we find is that out of this kind of latent space, those that are very persistent will kind of occupy more of the space up here. And then as they start getting more and more accumulation of evidence that starts pushing them towards making a different decision, we see that they kind of move into this other cluster space, which we kind of think about as like this win, stay, lose, switch, where as soon as you get no reward, you'll automatically switch to a new action. And then there's also kind of some randomness. People will start exploring and doing other things. And so while this is still kind of preliminary work and I don't have a lot more to say about this, we think that through the disentanglement of this model, we have a better or a more interpretable space that allows us to see some aspects of the underlying decisions that are being made. Whew. Okay, cool. So that was kind of the first part, this ability to take relatively low dimensional actions, right? So in this case, we're looking at the possible 3 different choices, but it's just a one-dimensional prediction, right? And so low dimensional, but still this multi-scale sort of framework shows us that we can, do a lot with these sorts of complex data sets. So next, we wanted to also understand whether or not these same ideas could be used in the study of animal behavior. And so to do that, we tapped into a really cool data set and benchmark from some folks at Caltech, including Yisong and others, and I guess he won't be talking about it next. But yeah, we really were excited about this challenge because it really hit on so many of the different things that I've been talking about, which is that you have the ability to understand things about local behaviors and what the animals are doing in a moment-by-moment basis, as well as they have global labels that tell you things about the strain of the mouse, the time of day, and these kind of more sequence-level activities. Okay. So, sorry, I'm getting very winded. It's hot. Oh, thanks. Appreciate it.
If you don't, I drink out of it.
Okay.
I don't feel sick.
Going for it. It's the end of the conference, right? So. Okay, sorry. Okay, cool. So, right. So we set out to test these sorts of ideas within this kind of higher dimensional setting. In this case, it's actually a multi-agent interaction challenge, and so in this mouse triplets part of their challenge, they already have key points that they've identified. So there's 12 key points on each mouse, and there's 3 mice within the cage, and so they're allowed to engage with each other, interact. There's a lot of different interaction behaviors that they track. And then in addition to having all the key points for all 3 mice identified, they also provide labels that are kind of moment-by-moment labels that are associated with the actual behaviors across all of the mice, and then give those large-scale labels as well. Okay. All right, and so then from this, as I kind of motivated at the beginning, the goal is to, and actually the challenge, you'll learn representations and then you actually submit those representations, and then they train a linear layer on the representations to read out 13 different tasks that vary in terms of whether or not they're frame level, so moment by moment, or sequence level tasks, so time of day mouse strain, and things like are the animals chasing, are they watching each other, grooming, etc. Okay, so I'm not going to spend too long here. I'm running out of time. That's to say that we entered into this challenge and we were number 3 on the leaderboard, so it was kind of cool. We were able to, with this, with this model and this framework that I've described, do a do a good job, be comparable with these other state-of-the-art methods on this task. But of course, we weren't finished there, or we started to kind of dig into what a good solution to the second challenge that I outlined at the beginning could look like. And if we can do that, and fold it into our framework, like what else can we do? Okay, so the challenge is that when we have free behavior, and we're at some point in time, we've observed the behavior in the past, and we're trying to predict what's going to happen into the future, there's actually many different possibilities, right? And so our ability to precisely track over many time steps into the future and predict from causal or from previous actions is really hard. So what that means is that as you start to make errors in future time steps, those errors start to accumulate very quickly, right? Because the choice that you made at the last time step kind of puts you off on the course. So just as a simple example, imagine that a mouse is kind of scanning around the room. It's a relatively simple task, right? That has some, simple structure overall, but the exact point at which they decide to turn their head back, is very unpredictable. And so overall, the dynamics might have some structure in this particular behavior, but the actual prediction of them in time is very hard. Okay, so what we do to tackle this challenge is a kind of a way of relaxing time and instead saying, over some future time horizon, can I predict a distribution over what that key point or what the possible actions that I'm going to take will look like? So what I'm sort of saying is, before we would have our latent embedding and then our predictor would try to actually predict the time series. But now we're going to look ahead in time and basically just create a histogram. So it's just a one-dimensional feature space for each of our key points. And now we have a distribution over the possible actions into the future. Okay, and Alex already talked about the Earth mover's distance and Wasserstein. So we're also going to leverage the sort of nice properties of this distance measure, and in particular, its ability to kind of robustify distance between, so if we took like a KL divergence and we have non-overlapping support between our distributions, then that can actually blow up, but the Wasserstein has a kind of nice smooth way of moving mass from one distribution to match a target. So basically, we'll have each key point converted into a histogram of possible actions in the future. And then our goal is to minimize the EMD between the ground truth distribution and our prediction, right? Okay. And this is just an example of kind of what it looks like if you were to take a time series from one of your key points, it's mostly zero, kind of, moving around, but looks kind of noisy. If we were to look at its distribution, we might be able to clearly see that it's centered around zero with some, small variance. Okay, so now we'll just basically, instead of using the mean squared error and predicting our time series into the future, we're now going to take still our same architecture that I showed before. We have the multi-scale temporal contrastive learning, and then instead, we're going to take the latents that we learn, we're going to pass them through a predictor, and in the end, our goal is to minimize the divergence between the predicted actions and the ground truth. Okay, so what's cool is that this works really, really well. And it's actually surprising. So I think in particular what we found is for these global prediction tasks, things like the strain of the mouse or the time of day, by relaxing this time varying prediction, which becomes overly myopic when the model can't actually predict into the future, it limits the amount of time into the future you can actually leverage into your predictive framework. So what we find is that with this, we can still effectively train the model, but have much longer future time horizons that we're using to build these distributions and solve the matching tasks. So this is just kind of looking at like taking out different pieces of the model, adding them back. So here, I'm just looking at, for a sequence task and for a frame level task, the total accuracy of the model. And what we find is that this histogram of actions approach has a massive effect on our ability to do long-term dynamical prediction. Okay, so then now we can kind of put this all together, and now I'm just comparing against all the top models on the leaderboard. We see a number of different variants of like a trajectory-based VAE, but then in addition to that, very complex models like BERT and PointNet and a temporal GPT model as well. And so what we find is that our model, across the board, makes very huge improvements on some of the tasks. And in particular, these long-term tasks are also kind of disentangled within the long-term space versus the shorter-term space. So it also has some nice interpretability in terms of being able to take the long-term and predict long-term things and short-term for the more smaller scale actions. And then here we're just looking at the performance of the models on these frame level subtasks, including a lot of things that have to do with complex interactions between the animals, so huddling or different forms of contact between them. Okay. So that was sort of the, the final piece, which is to say that when we put all of these pieces together, we can, we're now number 1 on the leaderboard instead of number 3, and grad students are happy and all that. So, okay. So in summary, I talked to you today about some work that we've been doing in understanding how to disentangle and model behavior at multiple time scales. I talked about this multi-scale temporal contrastive learning architecture called BAMS, and then described how we can also relax our action prediction framework through this kind of new way of doing future prediction by minimizing the Wasserstein divergence between the distributions. I also showed applications to human behavior, just showing that we can indeed do choice prediction on held out individuals, and that we're starting to see some interesting representations emerge that tell us some things about decision making. And then finally, talking about how this can be applied to animal behavior as well. Great. So thank you so much for your attention.